Hey there, everyone. It's Tynan Sylvester here. This is the RimWorld technical inquiry for those of you who are interested in the really nerdy details of exactly how this game actually works behind the scenes. So basically, what we're talking about today is pathfinding, spatial understanding, and nearest object finding, and reachability determination problems. It's basically a class of issues that have to do with, can I get from this point to that point? What's the closest X to me? What's the closest food? What's the closest bed? Can I reach this? Can I pass that space? And so on and so forth. Now, we've had solutions to these problems in place for a while now, but they weren't that great. I mean, they worked okay within the map of about 200 by 200, or maybe 300 by 300. But as the map sizes expand, these old solutions broke down. For example, the way to find the closest object of a certain type. So, say you're this muffalo and you're like, I'm hungry, I want to eat some grass. What's the closest grass? Well, to us, as humans looking at the screen, it's very easy to find because you just look and you see it right there. But for the computer, it's actually tricky. It depends on the data structures that it has access to do, or it has access to. The only data structures it had were a list of objects that was in each cell. So you could say, okay, in the cell, in this case, 44 by 176, what's in there? And you could get a list. In this case, it's nothing. This one would have, grass in it, basically, and nothing else. But that doesn't work that great when, that's awesome if you're already standing on grass or it's really close by. You could just like spiral out and try to find the first thing you take will obviously be the closest one because you're looking in a pattern that checks the first regions of the map first, or the closest regions first. But say you're in a situation like this where you're in the middle of this desert and the grass is really far away. You're going to end up checking a lot of squares. Or say it's an even worse situation, like say you're Emmy here. I'm going to make Emmy hungry. Now she's hungry, just with a little debug command there. And she's looking for food periodically. She's doing a little search behind the scenes for food. If she was checking every cell in a spiral pattern, or more technically a breadth first search, she would be checking every cell in the map every few seconds and checking every object in every cell, which would just destroy performance. Like, that is, you cannot do that, especially with larger numbers of creatures. So the other solution that we've been actually using is keeping a global list of every object of every type. So you'd have a global list of every grass in the map, of every character in the map, of every piece of rock in the map. This is pretty straightforward. It's really useful to have global lists, and they're easy to maintain because all you have to do is add something when it's created and remove it when it's destroyed. And those are pretty rare operations and not very expensive. So global lists are here to stay. But the problem is traversing them can be real tough. If you're checking for the closest grass, that means you're looking at every grass, checking the distance from you to every single piece of grass in the map, and just keeping which one is closest and then going to eat that afterwards. And that's actually what we've been doing, which sounds kind of nutty. But if on Alpha 3, there's a debug command, which honestly I forget which exact one it was, but I was actually getting bug reports because it would flash whenever something checked distance to something else, and it would flash like the entire map would just light up constantly because every animal was repeatedly checking every plant in the map for distance, which was crazy. Now your computers are insanely fast, and running through a list, like just a simple global list, is a real quick operation, but it's still not fast enough for as the map size increases. So you're hitting a performance bottleneck right there. So you have to restructure something if you're going to have bigger maps and more characters. Now, there's other related problems to that. You would have, for example, the global listing. It also misses things like this, for example. Or sorry, let me just get rid of that. Here, let's turn on God mode so I can just build stuff without restriction. And so say you're in this kind of situation here where Victor is looking for like someone to talk to. He's trying to find the closest character. So he's going to find Ryu here, even though Ryu is on the other side of this gigantic wall. And Emmy is quite close by. because, of course, in the global list, Ryu is actually closer. This would create a lot of really dumb behavior in certain circumstances, especially if he's working on a cook stove, and there's a pile of food just outside the wall, and there's another one that's close by, but not quite as close by, near in his room. He'll be constantly going out and coming back in. It just looks really stupid. So that's another issue that had to get solved. There's also the issue of reachability determination. So the pathfinding algorithm we use in RimWorld is the classic one. It's A star, which is used in a lot of games. And it's a really adaptable algorithm, and it's really quick, and it works really well. So you can see it running here. The game is showing all the cells that A star was inspecting as Victor was pathing from here to here where I'm telling him to go. And so it inspected all of these and these ones and these ones and these ones and these ones until it eventually got to the destination. You can see it actually inspected around both sides at once because it wasn't sure which side of this wall he should go around that would be closer. And it was actually a really close race. And then there's these ones in the middle that it never inspected. So you can actually turn that on if you turn on dev mode, and you can do this. It's kind of pretty because we've got the cells color-coded according to how distant they are from the origin point. But then you have situations like this. Like if you try to path into here, the way A star works, it won't know that you can't get in there. It'll actually check every single cell in the entire map, which will create a noticeable hitch in performance because it'll take like 30 milliseconds, which is longer than a frame, which is about like 15 milliseconds at 60 frames a second. And so the game would go and hitch every time someone tried to do that. So, that's a real problem. You can't have that happening, especially when there's a lot of reachability checks. So what you need is a solution. So the old one was we just essentially assigned a number to every cell for what, I guess, reachability group it was in. So you would start off, and the entire exterior could be group 1. And so they would just have that number 1. And we would flood fill out from some random point outside and fill the entire thing and just cover it all with 1s. And then any square that had not been filled with 1s, we would go and start flood filling from there. And this would all get filled with like a 2, for example. And there could be lots of interior spaces. Here's another one. So this would get filled by like a 3. And so if you want to find, can I reach this place, all you do is, before you even start trying to do A star, you just check, does their number match yours? So if Victor, if I ordered him to go in here, he would see, I'm on a square with 1. That's on a square with 3. I know I can't get there, so I'm not even going to try A starring. Because if I did, it would fill the whole, it would check the entire map and it just chug. So that solution has also been in place for a while. But it's a dumb solution because of the difficulty in rebuilding the data structure. In the old school way that RimWorld used for Alpha 3 and before, every time you had someone mining, they were digging a tunnel like this, square by square, or building a wall, laying it down as they do. Every time one of those went down, it would rebuild the entire map and refill every number, which was remarkably quick because I had a really nice flood fill algorithm going. But it's not acceptable, and more importantly, for larger maps, it falls apart. It's okay at like 200 by 200, maybe 300 on a large or a powerful machine, but it's not the kind of thing that scales well at larger map sizes, so once again, that's a bottleneck. So we've got all these problems, and to solve them, I have created what I'm calling the region system. So fundamentally, the region system is a new set of data structures. You think about how you think about, how do you as a human being think about space in the real world? You probably, if I ask you, can you reach, from this room to this room in your house? You're not going to think about it in terms of, 1 square meter steps on the floor. You're not going to think, okay, I can walk forward 1 step, and then I can walk forward 1 step, and then I can turn left 1 step, and then I can walk through the doorway 1 step, and this long series of operations, and then you eventually mentally arrive at your destination and realize, yeah, I can get there. You're not going to do that. What you're going to think is, okay, I'm in the bedroom, and then I can get into the hallway, and then I can get into the kitchen. And then that's only 3 operations, and you're there a lot quicker. But what you're really doing there is you're working through a different data structure on a higher level. You're not going step by step. You're going room by room. And so that is really what the game needed. That is what these guys needed, is a new data structure to look through, a new set of information that the algorithms could use. Because once you got your data structured well, the algorithms are usually pretty obvious. So that's that new data structure is these regions right here. And so each region is a small area of the map. It's a set of cells that can each reach every other cell in the region with no restrictions. So there's nothing that could possibly block anybody from traveling within the region. Ditto for here, ditto for here. If you look, you'll see that, say I cut this in half, now it's two separate regions. There's one on the right and there's one on the left. And there's one on the bottom. When I mouse over these regions with this debug view, it shows you all the other regions that are considered connected to that. So in this case, it's just the ones that are up, down, left, and right. So you get that sort of cross shape. But if you're around a wall, you're only going to see this one. You can only see the region to the left, region to the top, and region to the right, because of course you can't walk through this wall. So this region is not adjacent to the other one that's on the other side here. So that's pretty cool. And that means that we have access to some new algorithms. For example, let's see here. If you want to find the closest object, now instead of checking the global list, what we actually do is we just start checking through the regions. Each region keeps a list of the objects that are accessible from within it. And that means that, say we're like, what's the closest grass to me? We are using just the list of things that are in the local region first. So, if Victor is standing anywhere near some grass, he's going to see it because it's going to be in his region. But then if we don't find it there, then we look to the adjacent regions. And then if we don't find those, we look to the adjacent regions out from that. Now, it sounds similar to just checking every cell, but because the regions are so much bigger, it's a lot more efficient. You're looking through a lot fewer empty spaces. And remember, as soon as you find something, you just stop searching. So if you find it in the first region, you're going to never check any of the other regions, and you're going to do very, very little work, which is always what we want. It's very efficient that way. So here I'm going to turn on draw region traversal, and that shows when they're actually thinking about the regions that they're trying to find something in a region. So you're going to see these Muffalo. Here they go. So you see it flashes right there, right? And it flashes just that one region in blue. And it shows that they're looking for something. They're searching. And in this case, they're almost certainly searching for food. They're searching for the closest food. So I'm just trying to catch it right there. And they don't have to search beyond their first region to find it, which is super efficient. That's awesome. Because now all this other stuff, it doesn't matter how big the map is. It doesn't matter what else is going on or none of that matters. The data structure you're checking only has what's right around you. Now, if you don't find it right beside you, you can check in the regions adjacent to that, and then in the regions adjacent to those, and so on and so forth. And this is still quite a bit more efficient than the global search in a lot of cases, especially the worst cases. There's another extra bonus to that, which some of you, I'm sure, are already anticipating, which is, remember that problem I talked about with characters taking stupid paths when they're near walls, or especially long walls? Victor, get over there. So say Victor is looking for the closest person. Now what he's going to do is he's going to check his own region, which is this green one here. There's no one in it. Now he's going to check the regions adjacent to that. So he's going to go, no one in that one either. No one in that one. Oh, there's Ryu. I'm going to go chat with him. So now you found the correct answer to the problem, which is not actually what's the closest person. It's what's the closest person by my pathing distance. And so that totally solves all the issues with people going through walls or going around long walls to try to find things that they can't really get to quickly. So yeah, like it's another bonus basically, because once again it reflects the way you actually think about the world. Nobody thinks through global lists of everything and calculates distance to each one. Usually you're looking out from space by space and checking the contents of those spaces. Now in terms of reachability, there's actually another layer to this. This could have coexisted with the old fill the whole world with numbers system for determining if you can reach from A to B. But what we did instead was do the rooms not on the level of individual cells, but on the level of the regions themselves. So there are still a concept of rooms where each one is accessible within itself, but they're by region now. So here you can see, if you mouse over here, all these regions, each region here has a number attached to it, and that's of course, or not a number, it actually points to a data structure for the room. And the room has some special information, like, is it a prison cell? Does it touch the edge of the map? Does it have space open to the, open to the sky? Like these sorts of things. And this can be really useful because the AI often wants to know things like, does it touch the edge of the map? Because say animals, they only want to spawn on areas that touch the edge of the map. And that's really difficult to actually determine edge map touching if you're like pathing each time. It's really inefficient. But if you just maintain that data and you already know it, you're fine. Because you can just look it up. You've already got the data structured right there for you. So that's another bonus is being able to do rooms. Another issue, just going back to the perils of the old system and more of what motivated this. I told you about the fill the world with numbers approach to determining reachability, but I didn't tell you about one of the other issues with it, which is it can only handle one notion of, like, different characters can't be treated different ways in terms of what they can pass through. So for example, you fill the world with numbers. You want to say, can Victor get inside this room? Well, of course he can, right? Because he can just go through the doors. Now, if this squirrel is looking for some grass to eat, can it get inside and eat the grass there? Well, the answer is no, because the squirrel is not going to try to knock down the door. It's not psychotic. It's not allowed to do that in its current mode. But how's it going to know that, right? What it's actually going to end up doing, and what it was doing, was trying to path into the room and failing, which, as we've seen, is really brutal on performance. So the regions actually solved that quite well, because now each region knows who can go through it. So for these just regions that are just ground that you walk over, anyone can go through it. So that's very simple. Now, some of the regions are actually the doors. The doors themselves are little regions with their own little neighbors. So this one has those two neighbors, and this one has those two neighbors. And the doors have special properties that, like the character can query that region, being like, can I get through that region? Well, if you're an animal and it's a door and you're not psychotic, then the answer is no. If you are psychotic, the answer is yes, because animals are willing to bash through doors if they are in psychotic mode. If you're a prisoner and you don't have the key, or you haven't stolen it, or whatever, the answer is no. But if you have the key, the answer is yes. And so you're going to be able to search through the space according to what you're capable of passing through, what doors you're allowed to go through, which is really useful. So yeah, that's another bonus that the region system created. Is now we have this really powerful system for checking who can go through where and when and what. Another bonus is that it's more efficient with rebuilding. In the old system, by rebuilding I mean like updating the data structure. What we do is we don't want to rebuild all these regions. Like, we don't want to recalculate all 100 regions, right? Because the game will chug if we recalculate all that outdoor stuff too much. So we try to find the cheapest way of updating the set of regions in the game that we can whenever the map changes. So here, I'll try and draw region dirties, and that draws regions that have been changed. So here, if you just like, if someone was building a wall here, it would only change this region, and because the wall is completely surrounded by that region, none of this other stuff changes. The whole data structure stays the same. All we do is delete this region and rebuild just this little space here. Now, if you're doing something like, say, this, where you're actually revealing two regions to each other, and now they're combined. Before that was two separate regions, now it's one whole region. So here we take the space that was just opened up, we look at all its neighbors, look for the regions in them, delete them, and then fill out a new region from that space. And there are more complicated cases where, like, several regions are connected together in a frame, or these sorts of things. It's actually kind of a tricky problem if you're covering every case. But the upshot is that if you do it this properly, you never have to rebuild the whole map at once. You just rebuild whatever little spot has changed and then relink it back to the data structure that defines the rest of the game, or the rest of all the regions out here. And that goes for the rooms as well. Remember we had that giant room that covers the whole map. So here, I'll turn it back on so you can see it again. There it is. And so here, if we delete that, it's still the same color, which means it's the same room. And what it's doing there is it's realizing that this room already exists, and recalculating it would be a lot of work. And so it's going to just add newly dug out spaces or newly created regions to the best room that it can find. So here we have like another little region in here with its own little room, which you can't see because it's quite dull, but it's like gray, the outline. And then if we connect that, now it all takes the yellow color, because the yellow is the one for the outside. And what it's doing here is when you connect that, it determines how many regions are in each room that are being now newly connected together, and the one that has the most wins and fills in the other one with itself. And that way we avoid as much work as possible. Now, it doesn't really matter if they have the same number of regions. If you're connecting two spaces that were separated and about the same size, it's kind of irrelevant. But what we're often doing is things like this. Here's that room, here's the exterior, and we're connecting some kind of error. We're connecting a smaller space with the larger outdoor space, and the outdoor space will win because it has more regions in it, and so we can reduce the work we do just by recalculating the room connectivity in here and like tacking it on to the work that we've already done. So that's another cool optimization that helps you keep this whole data structure maintain at minimum amount of work. And so, yeah, I'll just talk about one final detail, which is how you actually find your neighbors. Now, I've been pointing out these regions and saying, okay, that one's connected to that one, and so on and so forth. And it's obvious when you look at it as a human what's connected to what. But actually doing that is a little tricky, especially when you're not rebuilding the whole thing at once. When every region can be deleted and rebuilt in any order in sort of random sequence, it can get really tricky if you're trying to query the square there and try to figure out what region is there and connect it to you and connect you to it unless you're already connected, and so on and so forth. So I think there's a system here of some technical interest for those of you who are interested, is how these things connect together. And it's actually by globally hashing these links together and finding the ones that match. So for example, this region here, consider what are the links that it has. Well, it has, looks like it has 5. One on the top, running the whole span here. One on the right, running almost the whole span, but not where that cactus is, because you can't walk through the cactus. One on the bottom, running, once again, almost the whole span except for the cactus. And then 2 on the left. This one running from the top left corner down to the cactus, and then another one from below the cactus down to the bottom left corner. So that's 5 spans. So you can say, well, so what? What's interesting about this is that this guy, his neighbor, has exactly this. It shares 2 spans with him. It also has this one starting just above the cactus going to the top, this one starting just below and going to the bottom. And that's kind of intriguing because that means we have these 2 things that can each independently generate their own little pieces of data. Just like they independently know from the structure of the world where they can connect on their edges. And they can use that to find each other. So what we actually do is we take each of these spans and we essentially reduce them down to a single number. This is a process called hashing. If you're a programmer, you're familiar with this. But the simple explanation is a number is, in computers, it's often like 32 bits. Say it's 32 bits. Well, the hash, or the link here has what information? It has a direction. It can be up or right. It has a length, which can be really no more than about 14, because that's the maximum edge length of these regions. It has a x-coordinate and a y-coordinate it starts at. So this one starts here, and it goes up for 6 squares. And so you can reduce all that information down into 32 bits. It's pretty easy. You would say, just hypothetically, you could store the x-coordinate in the first 8 bits, the y-coordinate in the second 8 bits, the direction in the third 8 bits, and the length in the fourth 8 bits. Now I actually do it a little bit different. I put direction in just 1 bit because it only has 1 bit because it can only be up or right. And the length is in like 4 bits because it only needs 4 because it can't be greater than 16 if my math is correct. Anyways, the point is you can put this into a single number. And we just do that. It's real quick. It's very easy. And then we actually keep a giant list of the whole map of every hash of every link in the game. It's in a big dictionary. And then if you want to find your neighbors, what you do is you build your own links, and then you figure out their hashes, and then you just look at that big list and say, is there anyone else who has put one in with that same hash? And this is a really fast operation. You're not actually doing anything geometrically. You're not querying this tile here to see if there's a region or that tile or something like that. All you're doing is looking up, does anyone else have this exact link? And you only have to do that once. If you're querying tiles, you'd have to check every edge tile that you have, and it's not that bad for just squares. But if you consider like sort of complex shapes with tons of doors, or regions that completely enclose other regions, like now this one's got like, I don't know, 5 different links or something, it gets more complicated. But just by hashing each link with its match on the other side, you can find each other pretty much instantly, and also know if the other guy is not there anymore or has been deleted or something. Because that can always happen, right? Because this whole data structure changes all the time. So yeah, that's pretty much it. There's also some tricky tech details in terms of keeping track of what's in each square and querying those efficiently. But I think I can leave that out for now. But yeah, that's the interesting part. The funny thing is, there's actually research papers on a technique called hierarchical pathfinding, which I don't even use. And that would be where when you're just finding a path from A to B, like, from here to here, you would find the path on the level of the regions first, and then path through those regions on the individual squares, and that reduces your pathfinding costs a lot. I actually haven't even done that yet. I've just used it for object search, reachability, these sorts of things. And I may do the full hierarchical pathfinding later, but for now it hasn't been necessary yet. But it's a really expandable data structure, and you can do a lot more stuff with it. Like you could say, okay, this region has dangerous, so don't go into it, right? So if there's a raider in that region, you just mark it as dangerous, and no one will go to eat food there or something like that. This is a lot more feasible than trying to do that by squares. I mean, you could have marked every cell near the raider as dangerous and then turn them off when he walks away, but it's a lot of work, right? You're talking about hundreds of operations every time this guy walks around. But with the regions, you just mark say 9 regions around him, and you're pretty good. And it even it works more naturally too, because if he's on the other side of a wall, then you're not going to mark the regions that are on the other side of the wall from him, because they aren't dangerous. He can't see them. So yeah, you can see a lot of possibilities for extensibility here, and it reduces a lot of problems that required global searches over the whole map to something local, which means that we'll actually hopefully be able to do larger map sizes in the future. So that's it. That's the region system. I hope you've enjoyed this intensely technical talk. And check out RimWorld. And I'm going to be continuing to work on this. And if you have any questions, you can ask me on the forums, probably the best place. And if I can find the time, I will do my best to respond, because this stuff is really interesting. So. Cool. Have a good day. I hope this was cool for you, and I'll see you guys later.